Hello, everyone. Welcome to the second lecture. For some of you guys, it may be your first if you happen to miss the first one. No biggie. I will be posting the recorded lectures on YouTube by tomorrow. The reason they happen on Thursdays usually is because that's my last lecture and I just put them all up at the exact same time. So as far as mastering chemistry and syllabus verification, I've had some people do that already. I've had a couple people get on to mastering chemistry. They haven't done the assignment yet, but they've at least gotten onto it. So make sure to do that before the week's end, because if you send me a message on Sunday night that says, oh no, my mastering chemistry code isn't working, and now I can't get in and do the assignment, that's going to be on you. So at least get into it to see that you can access it. And then if you have any issues, you can reach out to me before Friday's end. Okay, so we left off last time talking about significant figures. All those fun sort of quirky rules that tell us something about the precision of a number. So the more significant figures we have, the more precise our number is. So, you know, we want, as scientists, we'd want more significant figures. A couple of the rules, let's actually go forward here. So, you know, any non-zero numbers are significant. So the 3 and the 5 here are significant. Zeros that sit in the front of the base number are insignificant. They don't play into precision. Precision doesn't work going out to the left. Precision increases as we move to the right. Internal zeros are significant. So this one here, we've actually got a set of 4 sig figs. Internal zeros are significant, and then zeros that are at the end of the number after a decimal place are also significant. A scientist, if this 0 didn't mean something, if we didn't want to tell the reader that there was precision to the thousandths, we would just leave that 0 off. It isn't doing us any good except to let us know that we have actually measured out to the thousandth. Zeros that come before an actual decimal place are significant. So this 1 is significant. These zeros are significant here, and then these 2 zeros also are significant. So 5 sig figs here. Remember that you're going to have a unit of significance. So it's going to happen in a block or in a chunk. So you're not going to go, oh, this is significant, these aren't significant, and then this is significant. It doesn't work that way. It has to be all combined into one. So this last one here, this is that ambiguous thing. There's no decimal here. I can't read how many of these zeros are significant. I don't know. So the only thing I can go off of is the 1. So the 1 is significant. Everything else written like this, I can't explain if it's significant or not. This one's wrong. It says 2.9 and it says 3 sig figs. That should be 2 sig figs. Okay, let me 2 sig figs. If I wanted it to be 3 sig figs, I would write it as 2.90 times 10. Where am I? Times 10 to the 5th. Okay, the additional 0 would make it, or putting the 0 there would bring it out to 3 sig figs. This one here, let's talk about this. So 1 dozen is equal to 12. Can that definition or relationship become more precise if you have a better piece of equipment? No, it's a specific definition. So 1 dozen is always going to be equal to 12. Doesn't matter how good or bad your scale is. It's not a measured value, it's a counted value. This has unlimited significant figures. Okay, so we don't limit the number of sig figs we have here. This wouldn't be 1 and this wouldn't be 2. It's infinite. I'll show you some more examples of that if we hop back here. So exact numbers, unlimited sig figs, anytime we count discrete objects, like for instance, there are 3 students, I counted 3 students. I can't get better at counting that or more precise. Same thing with most conversion factors, all right? Most equivalencies where you have like 1 inch equals 2.54 centimeters, that's precise, that's exact. So it's sort of like saying, when I say that there's an unlimited number of sig figs, it's like saying 1.00000, and the zeros go on to infinity, inches is equal to 2.540000. Like my precision is all the way out to infinity centimeters. All right, they don't put all the zeros in there, but it's assumed. So anytime you're counting discrete objects or you're using conversion factors like this, we're going to say that there's an unlimited number of sig figs. So I'm going to give you a couple of these to mess around with. I want you to tell me how many sig figs these things have. Okay, so that's a decimal at the end. All right. That does say 4 dogs. Okay, I'll give you those. So 3207000 decimal. 0.0010010. 4 dogs and 400 with a decimal and a 0 at the end. I'll give you a minute. Okay, so this one here, it does matter that there is a decimal here. What that is indicating to the reader is that whoever measured this group or whatever this number, they are precise all the way to the ones place. So the 3, the 2, and the 7 for sure we know are significant because they're non-zero numbers. This 0 between these guys is also significant. Any internal zeros are significant. Remember, we can't be significant, we can't be precise, and then all of a sudden lose precision and then go back to precision. These zeros here are also significant. Why? Because they come before the decimal place. So zeros that come before a decimal place after the root number, we would say are significant. So in this one, we've got what, 1, 2, 3, 4, 5, 6, 7 sig figs. Lots of sig figs in that guy. All right, this one here. So what I like to do when I'm working with something like this is figure out where does the number begin? So the number actually starts here, right? These zeros in the front are just placeholders. So those don't bring any precision or significance. The number starts here. This is significant. This is definitely significant. The zeros in the center again, are significant. What about this guy at the end? That is letting us know that we are precise out to this decimal place. So that is also significant. 1, 2, 3, 4, 5, and 6. 6 sig figs. As far as the difference between these zeros and this 0, both of them are coming after the decimal place, correct? But these are coming before the root number. These are coming after the root number. So zeros that come after a decimal place but are before the number are insignificant. Zeros that come after the decimal place and after the number are significant. Hopefully that clears that one up. That, I find that one tricks people up a little bit. So this one, not significant. This one's significant. 4 dogs. 4 dogs, this is unlimited. Sig figs. Can't get better at counting 4 dogs, right? We can't have a half dog or a third of a dog. They're discrete objects. This number right here, we're not saying loosey-goosey, oh, you know, like, I can't even think of something. That piece of equipment weighs 400 pounds. We're saying, oh, no, that piece of equipment weighs 400 pounds to the 10th place. So precise, 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 precise. All of those are sig figs, 4 sig figs. Questions on any of those? You can throw it in the chat if you have anything. I want to show you one thing. So if you have a number like this, let's say we have 1 million. If I write 1 million like this, how many sig figs can we honor? Well, the only thing we can really honor is the 1, right? These zeros here are placeholders, so 1 sig fig. But what if I don't want to put a decimal here because not all the zeros are significant? What if only part of the zeros are significant? Like, let's say when I ran a calculation, I was allowed to honor 4 sig figs. So this is significant, this, and this are significant. Just these zeros are significant. How could I work around showing these are significant and these are not significant? The way you do that is you write it in scientific notation. Okay, so I can convert this to scientific notation, and I'm going to go 1.000, include just 3 of the zeros, times 10 to the, well, 6, is it? 1, 2, 3, 4, 5, 6, yeah, 6 times 10 to the 6. I'm not including all the zeros in my decimal. I'm just including the things that are significant. That's a workaround. So if you're like, well, I want some of the zeros to be significant, but not all of the zeros, change it to scientific notation. Great. Questions about significant figures? I will tell you right now, in this first chapter, you need to be honoring significant figures. My care for significant figures decreases drastically as the semester goes on. I'm not quite as anal about it, but in this first section, because I'm testing you on it, please make sure you're rounding to the correct sig figs. So let's talk about rounding. These are some rules that we learn, who knows, like 2nd grade, 3rd grade, I think, but always good to review them. So rules of rounding, if we're rounding in a calculation. When numbers are used in calculations, the result is rounded to reflect the significant figures of the data. So if I have like a really precise piece of information and I have a really crappy piece of information and I'm going to multiply those 2 numbers together, my final answer can only be as precise as my crappy piece of information. So we have to do a certain amount of rounding. So for calculations involving multiple steps, and hopefully this is familiar to you, don't round until the very end. Right? Don't round between steps, keep as many decimals as you can. This prevents rounding errors that add on top of each other. So how do we round? Use only the last or, excuse me, leftmost digit being dropped to decide in which direction to round. Ignore all other digits to the right. Round down if the last digit dropped is 4 or less. Round up if the last digit being dropped is 5 or more. So let's just talk about rounding really quick. I'm going to do too many of these. If I've got this number here, 4.4449. I want to round this to 3 sig figs. Okay. When rounding to sig figs, start on the leftmost, excuse me, the leftmost side. We're going to keep this number, we're going to keep this number, and we're going to keep this number, right? 3 spots. So I need to use the number that is just to the right to determine what happens with this final number here on the left. So what does the 4 tell this 4 to do? It tells it to stay. So my rounded value should be 4.44. You see how we turned a number that was 1, 2, 3, 4, 5 sig figs, and now we rounded it to 3 sig figs. Some people say, well, wouldn't the 9 tell the 4 to round to 5, and then the 5 would tell the 4 to round to 5? Don't play that game with yourself, because like, how far back do you have to go? If I have 4.44444449, and I want to round to 2 sig figs, do I need to take the 9 to the 4, make it 5, and go down? No, we just look at the number that's getting dropped on the right side. So I'll give you a number here. 3, I don't know why I like 3s today. 3, 6, 2, 7, 5, 8, 4. I want you to round this to 2 sig figs. Okay, so if we want 2 sig figs, this thing currently has 1, 2, 3, 4, 5, 6, 7, it has 7 sig figs. Where let's say that one of the pieces of information in the calculation only had 2 sig figs, so we only get to use 2 sig figs. So I get to have the 3 and I get to have the 6. What does the 2 tell the 6 to do? It tells it to stay. So this is 3, 6. And then what do I have to do with all these remaining spots? I can't take 3,627,584 and round it to 36. I have to round it to 3, 6, and then all of these spots get filled in with zeros. Okay. So 3,627,584 rounded to 2 sig figs becomes 3,600,000, not 36. Make sure to fill in your spots. So as far as applying this to calculations are concerned, there we go. Can you guys see the screen? It paused it for a second there. Yes? No? Maybe so, yeah, okay. So when running through calculations, you have to decide, are you doing multiplication, division, or addition, subtraction? Multiplication and division are like the inverse of each other, so they follow the same rules. Same with addition, subtraction. So with multiplication and division, the resultant of your multiplication or division will always carry the same number of sig figs as the factor with the fewest significant figures. So you're only as strong as your least precise piece of information. So if I'm going to take 2 numbers and I'm going to multiply them together, like let's say we're looking at this here. We've got 3 numbers instead of 2 numbers. This first guy has 3 significant figures. This second one has 5 significant figures. And then this final number only has 2 significant figures. So this is like an okay piece of information. This is a nice piece of information. This is kind of a crappy piece of information. You plug it into your calculator, and you may have asked yourself this before, like, how many decimals do I use when my calculator pops all this stuff out? Well, you really can only use whatever the least precise piece of information is. So if this has 2 sig figs, I have to round my final number to 2 significant figures. So this 45.0118 has to round to 45. And I know this drives some people crazy because they're like, look at how precise my number is. But it's not actually precise. This is sort of junk information because the starting numbers were great. The same. So when we're looking at these numbers here, we've got 4 sig figs and we've got 3 sig figs. When we divide them out, you know, sometimes your calculator will give you this like crazy long answer. You can only use 3 sig figs. So we get to keep the 9, the 6, the 5. The 9 tells the 5 to round up. So I'm going to give you just a couple of these. Let's say I'm in a place where I can't actually write, so I'll just type it. Okay, 4.992 divided by 8. So you tell me what that is. Hello. It's just one of those days. I'm like so close to calling this lecture. It's driving me crazy. Okay. Let me just finish up the thought that I was on with prefixes, and then I think we're going to call it. So if I want to make a unit bigger or smaller, I can just tag a prefix on it. With the British system, like if I want to make a unit bigger, I have to come up with a new unit, right? Inches, feet, yards, miles. In the British system, I just add one of these nifty prefixes. So there's a nice chart. Normally, I would have you guys memorize the prefixes, but because we're online, you guys get to use your notes. So you want to be able to use them, but you don't have to have them memorized. Where are you, you lovely prefixes? Okay, here they are. I wish they would put a base unit in there, but do you guys see this spot right between deca and deci? Right in there is your base unit, okay? So do you see how it goes from the tens place to the tenths place? Right in between this, we're gonna have our base unit. So these units are bigger, each by a factor of 10. So if I have my base unit right here, deca is 10 times bigger than the base unit. A base unit could be a meter, a liter, a second, a joule. So these get bigger. Deca is 10 times bigger. Hecto is 100 times bigger. Kilo is 1,000 times bigger. Mega is 1,000,000 times bigger. If you've, remember when you used to have an iPod and it had like megabytes on it? Now we've got terabytes on things. So a terabyte, 1,000,000,000,000 times bigger. If we move in the other direction, we get smaller, right? So a deci is 1/10 of your base unit. A centi would be 100th, like a centimeter or a century. A milli is not a millionth, it's 1,000, think millennial. A micro is 1,000,000th. Once you get out of the kilo to the milli, okay, the factors start increasing by 3 zeros. So here it's, right, we're increasing by 1 0. And then here we tack 3 zeros on. as we move up or down once we get outside of milli. One way that I remember these sort of smaller internal ones is King Henry died before drinking chocolate milk. That will get you through at least the internal ones, not the bigger ones and the smaller ones. So king is kilo, Henry is hecto, died is deca, before is your base unit. Okay, that's where you'd put your base unit. Drinking, deci, chocolate, centi, milk, milli. King Henry died before drinking chocolate milk. Know that the before can be any sort of base. So meter, liter, gram, second, joule. All those things can get prefixes tacked onto them. This thing, if it's written out like this, I like it because it makes converting between values really fast. So if I say, let's say that we're given 55 kilometers. And I want you to find this in meters. How many meters are in 55 kilometers? Well, kilometer is going to live over here at king, right? King kilometer. I want to get to meter. Meter is a base unit. There's no prefix on it. So in order to do that, I need to go from king to before. I take 3 hops. So let's do that. 1, 2, 3 hops to the right. That means I'm going to move my decimal to the right 3 places. 1, 2, 3. My answer will end up being 55 with 1, 2, 3 zeros. Meters. Real fast way to convert. What if I say, say we're given 872,000,000 millimeters. And I want to find kilometers. Okay. Start with your given information. Millimeter is over at the milk here. If I want to get to kilometer, which is over at the king, I've got to hop quite a few spaces, right? 1, 2, you do hop through the base, 3, 4, 5, 6 hops in the same direction. So we're going 6 hops to the left. My decimal lives here. I'm going to hop it over 1, 2, 3, 4, 5, and 6. So how many kilometers is this? It is 872 kilometers. That's kind of nifty, right? Much easier than converting from inches to feet to miles. That's one of the beauties of the metric system, is that because everything is on a base 10, it becomes as simple as just moving the decimal around. All right, so we're going to stop there today because my computer has made me super angry and I've got to figure out how to thread all these like mishmash lecture scraps together for a recording. So we will leave it at that. We will finish up chapter 2 next week. I do want you to get onto Mastering Chemistry. Please try and get onto it today or tomorrow so that I know if you're having trouble. If you have any individual questions, feel free to stay around and I can throw you guys in a waiting room and just pull you in one at a time. Otherwise, enjoy. It's Wednesday, right? So enjoy the rest of your week. So I will see you guys not Monday. I will see you in a week from today. I'll see you on Wednesday. Verify your syllabus. Check out lab quizzes, and Mastering Chemistry. Okay. So bye, everybody. Sorry for the the mishmash today.